Today we're going to be talking about the difference between simple distillation and fractional distillation. In principle, they're both exactly the same, but their setup is a little bit different, and one is more efficient than the other, and throughout the end of this video you'll understand why they're different. What I have currently in front of me right now is called a simple distillation setup. Now the reason it's called a simple distillation is because it only distills once, but there's no fractional column. Now you'll understand that better when we explain the fractional column distillation and what it exactly does. Now the general basis of the general setup of the apparatus is this, what you see in front of you. On the bottom is our thermal heating base, which warms up our whatever molecules that we're trying to separate. This right here is the collection round bottom flask where the actual molecule starting point is going to be. Right here is where the vapors rise up. Will rise up through this chamber right here and cool down and condense right down in this condensing tube. Now the way this works is that once this thing starts evaporating, the thermostat right here will start picking up the collection point, and once it hits the cooling jacket right over here, or the condensing tube, it will actually cool it back down into its liquid form. Now once it cools down in its liquid form, it will collect in this graduated cylinder, and we'll be able to know exactly the molecular weight and all that kinds of stuff that we collected from our sample. Now this right here is a water tube that connects right to our faucet, and the simple purpose of this is just to cool this tube down, so as the heat rises from here, it will recondense it back into a liquid form into the graduated cylinder. Now what's important though, inside the base inside here, inside the base right here, we have a stir rod. Now that's really important to keep the temperature equal in the molecule in the compound itself. Now what happens is if you don't have that stir rod, they'll have hot spots in it, and then when one thing is supposed to evaporate, the other will evaporate just because of random temperatures that you have inside the collection flask here on the bottom. All right. Now, once this process goes through, theoretically, we should have a sample of 1 and a sample of 2. Now, what we're going to be doing today between the two experiments to show you the differences, we're going to be separating cyclohexane from toluene. Now, cyclohexane has a lower boiling point than toluene does. Now, technically, or theoretically, if this works the proper way, when it gets to a certain temperature, the only thing that should be evaporating from here should only be cyclohexane. And then once all the cyclohexane has been evaporated out, the next thing that will be evaporated from here will be the toluene. And technically, at the end of it, we should have 2 separate compounds. Now, in simple distillation versus fractional distillation, that's not exactly the case. And we'll show you exactly why that happens. This right in front of me is a fractional column distillation. Now, as you can see, it looks very similar to simple distillation, but there is a little bit of a difference. The difference is this fractional column right here. Now, inside the fractional column, there's these glass beads. Now, what these glass beads do is that they collect the equal molar of the toluene and the cyclohexane. But as it cools the beads down, it will send the higher boiling point of the toluene back into the bowl and letting the cyclohexane evaporate back through and go through the condensing tube and back into the graduated cylinder to collect it. Now, why this is a little bit more efficient than the simple distillation is because of these glass beads right here. Now, when you have a simple distillation setup, when it evaporates, it's technically one plate. It evaporates up, goes through the tube, and comes back down. What this allows you to do is basically do the simple distillation, but in multiple steps. Now, technically, you can get the same results from a simple distillation as well as a fractional distillation. The only difference is in a simple distillation, at the end of the collection cycle, you have to rerun it again to get the same amount of technically quote-unquote theoretical plates to get the simple solution to compound here. Now, one run of this versus one run of that will give you a much purer sample in the fractional in the fractional distillation versus the simple distillation. So this is why this technically is the same thing, but this just gives you a more efficient, more proper way of doing it instead of having to run the sample over and over and over again. Now just go through the apparatus just like the simple thing. You have your heating element right here, just same as a simple distillation. You have your round bottom flask where you actually put your compound in to heat up. Now in our case, we're using toluene and cyclohexane. We have, now this is our fractional column. Now this is what's different between our simple distillation and fractional distillation. And as you can see, the glass beads in here is what collects and helps us kind of increase technically the theoretical plates. Then everything else is exactly the same. You have your temperature, thermometer here, so you can measure your volume versus your temperature. You have your condensing tube, which cools your vapors down back into a liquid form, and then the vapors, or the liquid form, will drain back into the collection tube here. Now, technically, this should give us a much more pure sample than the simple distillation. So if we're running our cyclohexane toluene equal molar solution, the first thing we should have is a much more higher concentration of the cyclohexane. And after we run that, then we should have an equal molar, or a very high concentration of toluene after we have evaporated all the cyclohexane out of the compound. currently we are running our experiment right now, and as you can see, we have set the temperature about between 100 and 120 degrees, and we also set the revolutions on here to keep this mixing. Now, as this is going through its process, what will happen is this will start to evaporate. Once it evaporates and gets to this tube right here, we'll be able to monitor the temperature using this thermostat, or thermometer, I apologize. Now, what is important for this thermometer is to make sure that the end of the thermometer is right there by the beginning of the condensing tube. The reason you want to do that is so you know the accurate temperature of the vapors as it comes through the round bottle flask. Now, once it collects in here and goes down the collection tube, what we'll do is we'll basically collect the first 3 samples and put it in a vial, and from there we'll be able to run the GC on it and see what the actual concentration of this technically cyclohexane that we got. Once we do that, we'll basically keep collecting to see exactly how much volume of cyclohexane that we collect, and then when we measure from there, we'll be able to know the theoretical plates or the efficiency of our system. The temperature itself is going to slowly start rising up to 80 degrees. Now, 80 degrees technically is our boiling point for cyclohexane. Now, it can be 81, it can be 79. It's a very range of that because technically speaking, we don't have exactly the most accurate thermometer that we would have in a laboratory, but it's a very good range to collect it. Once we've collected it at that temperature, we know that that's only cyclohexane because toluene boils at a much higher point. All right, so much like simple, we're running the apparatus exactly the same way. We got the rotation of the magnetic stir bar here makes sure that the temperature of the molecules of the compound stays exactly the same. It's going to be evaporating through the fractional column, much like the simple distillation column, but upset not having goes directly through here, you're going through the fractional column. Now, as you can see, the glass beads in here are starting to get a little bit moist. Now, that's what you want. You don't want them basically drowning in this stuff. You just want it moist, because if they're drowning, you're distilling way too fast, and the concentration at the end of it is going to be altered by how much, because you could have not just cyclohexane in it, but you could also have a molecule of toluenes in there as well. Now, as you see this moistening up, now, what will happen is as the cyclohexane and toluene is evaporating through here, it will come through and hit these beads. Now, what these beads do is cools down the structure. Now, why would you want to do that? Well, we know that cyclohexane and toluene have 2 different boiling points. Now, if they have 2 different boiling points, then if this was a perfect world, then the only thing that should be evaporating through here is only cyclohexane and none of toluene. But technically, that's not. We don't live in a perfect world. So what's happening is that both things are boiling because the temperature in here is not exactly the same. There'll be hot spots in one area or the other that will boil the cyclohexane and toluene up at the same time, even though they have 2 different boiling points. So what these glass beads do is it cools it back down to where toluene becomes a liquid again and drops back down into the collection flask. And the cyclohexane will keep going up through the collection flask into the condensing tube and back in through the test tube for collection. We're at the fractional distillation right now, and as you can see that everything's starting to work. At the bottom of our collection graduated cylinder here, we can actually see a couple of drops coming here. Now, for us to get the first sample for our GC, we want to get the first 20 drops. So right now we're about 14, 15, 16, 17, 18, 19, and 20. Now we can stop collecting here and get another flask. The temperature right now has been collected to 80 degrees. Now this should be the boiling point of cyclohexane. Now what we're collecting here in our flask right now should be cyclohexane. Now we're going to keep collecting until the temperature gets to about 120 degrees. Now once we get it to 120 degrees, we're going to stop collecting and we'll be able to get the volume and exactly how much we were able to collect our sample from our simple distillation. And we're going to keep collecting the volume sample as we go on. Now we're going to run this as well as what we collected from the fractional distillation in the GC to see what our mixture and what our concentration of each of our 2 components is. So 80 degrees Celsius is the mark that we're looking for, and as you can see, we are within 1 or 2 degrees within that 80 degrees. Now it's going to stay at this point until technically all the cyclohexane has been boiled out of this out of this compound. Now once all the cyclohexane compound has been evaporated out, what's left is toluene. Now, since toluene has a much higher boiling point than cyclohexane, the temperature from here, as it plateaus, will skyrocket a little bit further up the chain. Once we know that things started skyrocketing up, it's basically evaporating only toluene. Through our fractional distillation, we have collected about 20 milliliters. Now, we can stop collecting right now, start putting it all together, and start wrapping up the apparatus. So at this point, what you want to do is you want to turn off the heat on your heating element, and then you'll be able to collect your sample. See the temperature right now is at basically between 80 to 85 degrees, and we have collected 20 milliliters of our cyclohexane. After we collected our first sample, we have collected up to 20 milliliters of our second distillation for our fractional distillation. Now what we're going to do is we're going to go ahead and add some of this 20 milliliters over here to the GC so we can see the concentration at this point. Now the next time, the third time we're going to collect the vial is when the temperature shoots up beyond the 85 degrees and we know that we're collecting basically cyclohexane. I'm sorry, toluene, not high cyclohexane. So by the end of our experiment, we currently have 4 vials. 1 vial that we collected for our sample of simple distillation, and then we have 3 vials that we collected at 3 different points for fractional distillation. Now, in simple and fractional, these 2 vials right here were the first few drops that were collected. This right here is after the temperature got to 85 degrees, and this was after the temperature reached 120 degrees. That way we can kind of see what the concentrations of each is at different steps through the fractional distillation. Now we're going to load our sample into the GC. Now, what we do is we have a syringe right here which we collect the sample in, and then our vial that we collected the sample from. All you gotta simply do is insert the syringe inside the vial, pull up ever so slowly to make sure not pull the plunger all the way out, because you'll basically get liquid at the other end of it. Now, once you have done that, you come over here to your GC machine, and you have 2 different sections. You have A and B. You can insert it into whichever one the computer wants you to insert it to. You just plug it directly in there, plunge it down, and the computer will spit you out a result, and that way you can compare the concentration levels of each of the cyclohexane or toluene. Am I going to A or B, Dr. Mondre?
Go into B, and then you use that, and I'll go ahead.
So we insert the syringe all the way down, and whenever you're ready, put the plunger all the way in. Once you do that, the computer will do its work. And then you repeat this process again with each of the different vials. This right here is the graph that the GC gave out us for our first sample of our fractional distillation between toluene and cyclohexane. Now, as you can see, there's 2 peaks right here. A big peak right here and a small peak right here. Now, what these 2 peaks correspond to is the actual molecules of either cyclohexane and toluene. Now, since we went through the fractional column, the first sample that we collected should technically be majority of cyclohexane, not toluene, which is represented by this graph right here. This graph, on the other hand, or this bump right here, is basically representative of the toluene mixture. Now, what this basically tells us, even though we have a high concentration of cyclohexane in one of the in the sample itself, but there is a small portion of which is toluene, and this toluene right here can be further filtered out with further distillation. This graph right here is from our second collection point when we collected the second vial. Now, as you can see, the graph is very similar to the first one, except that now toluene has a much higher bump than it did before. Now, what this means is that when we got to this point, though majority of what we were distilling was cyclohexane, the components of toluene has gone up as well. Now, it's simply because the temperature at this point has gotten up a little bit, and so since we're still distilling out cyclohexane, we are also distilling out a good portion of toluene as well. This graph here is from our last and final collection, our third vial, if you will. Now, as you can see, the different peaks have basically reversed from our first collection sample. Now, this is true because at this point we shouldn't really have any more cyclohexane left, but we should really have more toluene left. Now, as you can see, though, there's still not a 0 to 100%. There's still a few little bit of remnants left behind. But as the fractional column goes through its distillation process, you can see from the previous 2 graphs that the bump just starts slightly going towards the right. So now we have cyclohexane here, which is a much smaller portion, and then toluene here, which is a much bigger portion. This graph was printed out by our GC for our simple distillation. Now, as compared to the fractional distillation that we just discussed, as you can see, the peaks are nearly identical. Even though they're not exactly identical, they're much more similar to each other than they were in the previous graphs. Now, the reason for this being is because of the difference in the inherent difference between simple distillation and fractional distillation. Now, at your first run, when you do your simple distillation with 1 theoretical plate, this is basically the constituents of your molecule. Even though there's a higher percentage of cyclohexane in there, there's still a good portion of toluene in it as well. Now, to get this to a more pure sample, the simple distillation will have to be run over and over and over again, and then this graph would match very similar to the graph 1 from our fractional distillation.